Now let's see one more example, and we shall try to decompose this table into third normal form based on this definition. Instead of going through second normal form and then transfer dependencies, we shall use this formal definition and try to decompose it. Now first of all, let's try to test whether the given table is in third normal form or not. So in order to test it, you are supposed to find out what is the candidate key. So how can you find out the candidate key? See this. Now B, E, D are present in the right side. So B, E, D are present in the right side. Now if you see this, only A and C are not present in the right side of any functional dependency. Therefore they should definitely be present in the candidate key. So A and C should definitely be present in the candidate key. Let's try to find out if AC plus is enough, which means if AC plus itself is going to be a candidate key or not. So okay, I mean to say if AC is going to be a prime candidate key or not. So for that reason I am finding out AC plus. Then what do you get? AC, because A is there and A is here, I can include B, and because B is here and B is here, I can include E, and because C is here and C is here, I can include D. Therefore AC is able to cover all the attributes, which means AC plus is containing all these attributes. So AC can be a candidate key. Now you cannot remove either A or C from this, and if you add anything to this, that will become redundant. Therefore AC is the only candidate key for this table, right? Why? You cannot delete anything from this, or you cannot add anything to it, right? So AC are necessary to be present in the candidate key, and also they are sufficient. Therefore it is the only candidate key you get. So think logically, you will understand it. Okay. And now based on this definition, we are supposed to find out what are the key attributes and what are the non-key attributes. So A and C will be key attributes, and remaining all will be non-key attributes. What are the non-key attributes? B, D and E are the non-key attributes. Got it? And what is the super key? AC is the candidate key, therefore it is also a super key, and any superset of AC, which means ACB, ACD, ACE, AC, anything containing AC is a super key. Got it? Okay, now let's go to this definition. Let's take each one of the FDs and see whether they are satisfying these two conditions or not, any one of these conditions. Now if I take A determines B, the left side is a super key, isn't it? Oh, left side is not a super key. See this. If you take A determines B, the left side is not a super key, therefore it is failing the first condition. And if you see the right side is not a prime attribute, it is a non-prime attribute, isn't it? Therefore this functional dependency is failing both the conditions, right? So it is not, therefore this table is not in third normal form. Why? Because of this FD as of now. That is what we discovered. As and when we discover this, split the table, right? So how do I split the table? Find out A plus. If I try to find out A plus, it is going to be A, and then because of this I am going to get B, and because B is present here and B is present here, I am going to get E. Got it? Okay. Now what you should do is split this table A, B, C, D, E, A, B, C, D, E into two parts in such a way that A is going to take with it B and E, B and E, and you leave the remaining there. So A, C and D, and also you have to include B as well here. Okay. So A and C, right? Yeah, it is enough. So you have to always see that the original candidate key is maintained, which means AC is maintained somewhere, so that when you are merging the tables, it will be lossless merge, which means this decomposition will be lossless. And also see that there is an intersection between these two in such a way that that intersection is going to be a key for one of them. So in this case, A is the intersection and A is the key for this primary key or candidate key. Therefore this decomposition is lossless. Now after dividing them, just reallocate the FDs depending on where they are applied, and again test these two conditions on all the FDs. so that you will understand whether this table is in third normal form or this table is in third normal form. If they are not in third normal form, again you are supposed to decompose it. Okay, now what is it? A determines B. So where is it applicable? It is applicable here. A determines B, and B determines C is also applicable on this table, and C determines D is applicable here. Got it? Okay. Now if you observe this, and anything is on this table, A, C, A, B, C, D, E, A, B, E are here and A, C, D are here. Okay, fine. Now let's try to take each one and let's see. Now if you observe this, AC is the candidate key for this table, right? Because AC plus is going to give you D. Yeah, if you observe this, AC is the candidate key for this table. Okay, and now let's see whether this table is in third normal form or not. How can you test it? Just take this one and see. So where is it? Here. Yeah, X is a super key. Is left side a super key? It is not a super key. Now see if Y is a prime attribute. Is right side a prime attribute? No. D is not a prime attribute. Only A and C are prime attributes. Therefore, this FD is failing these two conditions, right? So what should you do? Again split this table in such a way that C plus should be in a different table. When I find out C plus, I am going to get CD, which means C is going to take with it D, and so AC will be remaining there. So AC will be in one table and CD will be in the other table, in such a way that C is the primary key for that. Now what is the FD applicable on this? C determines D. Now if you see this, for this table, C is the candidate key and the left side is definitely a super key, and so we are satisfying the first condition, and so this table is in third normal form. We don't have any FDs on this, therefore it is definitely in third normal form. Only FDs are going to fail the third normal form. If we don't have any FDs, it is definitely in third normal form. Now if you look at the other side, now A is the candidate key. Now if you take this first functional dependency, the left side, this one is already a super key. Why? If A is the candidate key, then definitely A is the super key as well, right? So there is no problem with this FD. Now let's see the next one. B is not a super key, which means the first condition is failing, and E is also not a prime attribute, which means the second condition is also failing. E is a non-prime attribute. Therefore, because of this FD, this table is not in third normal form. So how can you make it into third normal form? Decompose it. Now decompose this in such a way that find out, see this is the FD which is failing us, right? So find out B plus. Now if you find out B plus, you are going to get BE, right? So BE, what does it mean? B is going to take with it E, and whatever is remaining you write it here. So what is it? AB will be remaining here. Therefore there is a new table BE with B as the candidate key, and a new table AB with A as the candidate key. Now if you see the application of these FDs, A determines B will be applicable here, and B determines E will be applicable here, right? Now this is the candidate key for this table, and the first rule is satisfying. So what is it? If you take this FD, left side is a super key, therefore this is in third normal form, right? And this is the candidate key for this table, and there is only one FD, so check it. So now the left side of that FD is super key, therefore this is satisfying the first condition, and so this table is in third normal form. Got it? So the original table, when it is split into many tables like this, so what are all the tables you got? One is AC, other is CD, other is AB, and other is BE. If you split it like this, the table is finally going to be in the third normal form. So in this example also, we didn't care about partial or transitive dependencies. We have checked only these two rules, and also we didn't make the table into second normal form before going for third normal form, right? So if you see this, yeah, finally anyway the inner meaning will be eliminating the partial dependencies and transitive dependencies without mentioning them, and also the order we followed need not be eliminating the partial dependencies first and then the transitive dependencies. In fact, if you see this, yeah, first one, we this A determines B is a partial dependency, right? So we eliminated it, and then after that C determines D is also a partial dependency, so we eliminated it. Now coming to the other side, B determines C is a transitive dependency, and so we eliminated it, right? So the order in which we did is anyway here partial dependencies and then transitive dependencies, but it need not be that way all the time. For example, if you would have taken let's say B determines E first, if we had tested this one first before this, then we would have split the table in such a way that B plus we would have found out, and we would have split the table that way, which means we would have eliminated the transitive dependencies first. So that depends on the order in which you check the FDs. Therefore there is no rule that first eliminate all the partial dependencies and then the transitive dependencies. You can take the elimination in any order, which means you can eliminate some of the partial dependencies and then some of the transitive dependencies, and again partial dependencies, and again transitive dependencies. Whatever way you do, finally you should see that all the transitive dependencies are eliminated and all the partial dependencies are eliminated. So either you follow this method or you follow the earlier method. So coming to second normal form and then the third normal form, otherwise you use this and get into third normal form. Okay, fine.